Welcome back. In the previous episode, we explored how mountain waves, lee-side lows, and cyclogenesis affect local flight conditions. Now it's time to zoom out and explore how pressure systems shape global weather and what that means for aviation around the world. Let's begin at the equator. Here, intense solar heating causes warm air to rise. This creates a belt of low pressure called the Intertropical Convergence Zone, or ITCZ. It's where trade winds from both hemispheres meet, bringing towering clouds and intense thunderstorms. The ITCZ shifts with the seasons. In July, it moves north. In January, it moves south. That's why tropical rain belts and thunderstorms aren't fixed, they follow the sun. Pilots flying in these regions must watch for convective activity and heavy rainfall. The rising air from the ITCZ eventually cools and spreads out toward the poles. Around 30 degrees latitude, it sinks, creating subtropical high-pressure systems. These are known for their clear skies, stable air, and dry conditions, perfect for VFR flights. These subtropical highs are responsible for the horse latitudes, regions of calm winds and clear weather. They form the basis of the Hadley cell, a major global circulation pattern that moves energy from the equator toward higher latitudes. Now let's talk about the Ferrel cell, found between 30 degrees and 60 degrees latitude. Here, surface winds blow from the west. These are the prevailing westerlies. They dominate mid-latitudes and explain why most weather systems in these areas move west to east. At around 60 degrees latitude, warm air from the Ferrel cell meets cold polar air. This clash creates a polar front, a zone of low pressure and storm development. It's the breeding ground for mid-latitude cyclones that impact Europe, North America, and beyond. Above the polar front flows the polar jet stream, a high-speed river of air that steers storms and separates air masses. For long-distance flights, the jet stream is both a helper and a hazard. Catching a tailwind saves fuel, but hitting turbulence can be rough. Now we reach the poles. Here, cold, dense air sinks, creating polar high-pressure systems. These systems are generally stable and dry but can also produce strong surface winds and dangerous icing conditions, especially in Arctic operations. So we have three major cells in each hemisphere. Hadley, 0 to 30 degrees. Ferrel, 30 to 60 degrees. Polar, 60 to 90 degrees. Each one helps circulate air, energy, and weather around the globe. Let's connect this to pressure belts. Around 0 degrees and 60 degrees latitudes, we find low-pressure zones due to rising air. Around 30 degrees and 90 degrees, we find high-pressure zones where air is sinking. This pattern repeats in both hemispheres and drives global wind flow. Trade winds blow from east to west in the tropics. These easterlies help steer hurricanes and tropical storms. Between 30 degrees and 60 degrees, the prevailing westerlies take over, moving systems from west to east, just like most weather in Europe and North America. Pilots crossing oceans or continents must understand these flows. Knowing where the jet streams, pressure zones, and storm tracks are can save time, fuel, and stress. Long-haul flight planning always includes wind and pressure system forecasts. Now let's talk about seasonal shifts. In summer, land heats faster than ocean, creating monsoonal low pressure. In India and Southeast Asia, this drives massive rainfall. In winter, cold land creates high pressure, driving dry winds outward. Another seasonal example, the Siberian High, a massive cold high-pressure system over Asia in winter. It pushes dry, frigid air southward, affecting weather across China, Korea, and Japan. Pilots in these regions must plan for dense air and freezing conditions. In the southern hemisphere, global patterns are more stable due to fewer landmasses. The roaring 40s, furious 50s, and screaming 60s are bands of intense westerly winds that dominate high southern latitudes, tough regions for flying and sailing. Let's shift focus to global pressure anomalies. El Niño and La Niña are shifts in pressure and ocean temperature across the Pacific. These alter the jet stream, storm tracks, and rainfall patterns across multiple continents. Their impact on aviation is massive. El Niño often brings stronger jet streams and more turbulence across the Pacific and North America. La Niña, on the other hand, can shift storm tracks and create stronger cyclones in the western Pacific. Seasonal forecasts are key when planning long-term operations. Understanding the climatology of pressure systems helps anticipate seasonal risks. Pilots flying in Africa during harmattan season should expect dry, dusty winds. In Australia, the subtropical ridge dominates in winter, bringing clear skies and cool nights. And don't forget volcanic activity. A strong eruption can inject ash into the atmosphere, altering local pressure and circulation patterns. Ash clouds are invisible on radar and extremely dangerous to aircraft engines. Always check NOTMs and SIGMETs in volcanic zones. Satellite weather imagery is a powerful tool. You can visualize high and low pressure systems, track tropical storms, and follow jet stream patterns. Combine that with surface and upper air charts, and you'll get the full 3D weather picture. Speaking of vertical structure, pressure systems aren't just surface features, they extend through the troposphere. A surface low is often linked to an upper-level trough. A surface high usually aligns with an upper ridge. Pilots need to see both layers to fly smart. Understanding pressure aloft is critical for choosing altitudes, avoiding turbulence, and riding tailwinds. It also helps explain why weather sometimes lingers or clears faster than expected. The atmosphere is a layered, moving system, not a flat chart. Let's recap. Global circulation is driven by heating at the equator and cooling at the poles. Hadley, Ferrel, and polar cells create repeating pressure patterns. Jet streams guide storms and affect flight efficiency. Seasonal and regional systems like monsoons and the Siberian high add complexity. El Niño and La Niña cause global-scale shifts in pressure and weather. By mastering global pressure systems, you unlock the final piece of the meteorological puzzle. It's not just about local weather anymore, it's about anticipating patterns, reading the sky, and making decisions like a true aviator. In our next episode, we'll start a new topic, altimetry. We'll explore how pressure affects altitude readings, how altimeters work, and why setting the right pressure reference is vital for safe separation and terrain clearance. See you in Meteorology number 09, Altimetry, Part 1.